Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Right now, roughly 600 kilometers above your head, there's this discarded, totally dead metal tube from the 1960s just plummeting toward Earth.
Yep. Just falling out of the sky.
And the crazy thing is, orbital dynamicists and, solar physicists couldn't be happier about it.
Oh, they are absolutely thrilled.
Right, because that specific piece of ancient space trash is currently rewriting the fundamental mathematical laws of how our sun interacts with our planet.
It really is, it's a profound irony of the modern space age, honestly.
How so?
Well, think about it. We launched these multi-billion-dollar observatories, right?
Yeah.
Packed with, the most advanced optical and magnetic sensors humanity has ever engineered.
Just specifically to study the sun.
Exactly. Yet, for some of the most critical data regarding how our star physically manipulates the Earth's upper atmosphere, we are completely reliant on these passive, inert husks of metal.
Stuff that hasn't had a functioning battery since, the Apollo era?
Right. They are unintentional, but basically perfect scientific instruments.
It's wild. So today, we're getting into how a dead rocket stage from 60 years ago is suddenly the key to mapping solar physics. But to understand that, we kind of have to look at the environment where this is all happening.
The physical space itself.
Because when you stand outside at night and look up, the space immediately surrounding Earth appears, serene.
Sure, it looks like an empty, frictionless void.
Right. But low Earth orbit, that shell of space stretching roughly between 400 and 2,000 kilometers in altitude, is essentially a chaotic, hyperkinetic shooting gallery.
Totally. And it is completely at the mercy of solar weather.
So let's dismantle that first idea. Space isn't a static vacuum.
No, not at all. The perception of space as a static vacuum is the very first thing we have to throw out the window here. Low Earth orbit, or LEO, is a fluid, dynamic, and intensely packed environment.
It's basically prime real estate.
It is the absolute prime real estate for human infrastructure. I mean, if you're looking at Earth observation or synthetic aperture radar for military surveillance.
Not just the internet.
Right, the massive proliferation of internet mega constellations. You're looking at LEO.
And because it's the prime real estate, we have spent the last 6 decades absolutely trashing the place.
We really have. It's a mess up there.
And we aren't just talking about active satellites, right? We're talking about thousands of spent upper rocket stages, dead satellites that suffered catastrophic failures.
Sensor covers, explosive bolts, you name it.
Yeah, plus millions of fragments of just straight-up shrapnel from previous orbital collisions.
And the kinetic reality of that debris is what makes LEO so precarious. Because to maintain orbit and resist the immediate pull of gravity, objects at that altitude have to travel at immense velocities.
Like how fast are we talking?
Roughly 7 to 8 kilometers per second.
Per second? That's insane.
Yeah, it's over 25,000 kilometers per hour. So at those velocities, the kinetic energy equations are, they're terrifying.
I can imagine.
Like an impact from a piece of debris the size of a marble carries the physical kinetic energy of a bowling ball hitting you at 60 miles per hour.
Oh, wow. From a marble.
From a marble.
Ow.
And an impact from something the size of a grapefruit is roughly equivalent to a detonating hand grenade.
So a collision isn't just like a fender bender on the highway.
Not at all. If two objects hit each other up there, they don't just dent. They undergo what's called hypervelocity fragmentation.
They basically explode.
They instantly vaporize and shatter. So you turn two large trackable objects into tens of thousands of new, lethal, untrackable projectiles.
Which is the foundation of the cascade risk, right? The domino effect.
Exactly. One dead weather satellite and one spent booster stage cross paths, and in a microsecond, they cease to be two objects. They become an expanding cloud of hypervelocity shrapnel.
And then what happens to that cloud?
Well, over the course of a few months, orbital dynamics will take that concentrated cloud and smear it into a shell of debris that encompasses the entire globe.
Which just geometrically increases the probability that those fragments will intersect with other active satellites.
Right, creating even more fragmentation. It's a chain reaction.
Yeah. Okay, but hold on. If we know LEO is a shooting gallery and we have global radar networks tracking all this debris, why aren't we just clearing the chamber?
Well, simply knowing the exact trajectory of a piece of shrapnel doesn't neutralize its kinetic energy.
Right, because robotic capture tech is still highly experimental.
Exactly. It's very much in its infancy.
So doesn't tracking just give us a, high-definition, real-time view of our own impending collisions? Like, we're on a crowded highway blindfolded with no brakes.
It's a great analogy, but tracking doesn't neutralize the debris, no. However, it is currently the only operational shield we have, because our valuable assets possess something the debris doesn't.
Which is?
Propulsion. The Space Surveillance Network uses these massive ground-based phased array radars and optical sensors to track tens of thousands of these objects.
Constantly updating their orbits in some massive database, I assume.
Right, and by running sophisticated conjunction assessments, basically calculating where every single object will be days in advance, we can predict intersections.
So it's entirely about defensive maneuvering.
Precisely. The debris is purely ballistic. It just follows the cold laws of orbital mechanics.
It can't dodge.
It can't dodge. But an active billion-dollar imaging satellite has thrusters and a finite reservoir of fuel.
So if ground control gets an alert that, say, a fragment of a 1999 rocket explosion is going to pass within 100 meters of their satellite in 48 hours.
They calculate a maneuver, they fire the thrusters, burn a precious fraction of their fuel, and alter the satellite's velocity just enough to change its altitude.
Allowing the bullet to just pass safely by.
Exactly.
But that entirely relies on the prediction being flawlessly accurate, right? I mean, if your orbital mechanic model's wrong by even a tiny percentage, you might maneuver your satellite directly into the path of the debris.
That is the nightmare scenario, yes.
And this brings us to the massive fiery variable that makes predicting these orbits so incredibly difficult.
The sun.
The sun. Because the model isn't just about gravity and velocity, the model is constantly being warped by solar weather.
This is where we cross from pure orbital mechanics into solar terrestrial physics. We tend to think of the Earth and the sun as like isolated bodies, separated by 93 million miles of empty vacuum.
Right, just floating in the dark.
But they're deeply physically connected. The sun is not a static light bulb. It is an active, shifting magnetic dynamo.
And it operates on a cycle, right?
Yeah, a roughly 11-year cycle of intense activity and relative calm.
Let's look at the engine of that 11-year cycle. When we talk about solar maximums and minimums, we're basically looking at the sun's magnetic field tangling and untangling itself.
That's a good way to picture it, yeah.
And the visual indicators of this internal chaos are sunspots, right? Those massive, magnetically intense regions on the solar surface that appear dark.
Those sunspots are the focal points of magnetic stress. When the sun moves toward its active phase, which, by the way, we've been seeing recently, the magnetic field lines become incredibly complex.
They get all twisted up.
They twist, they snap, and they reconnect. And when they do that, they release staggering amounts of energy into the solar system.
And it isn't just visible light hitting us. The sun is essentially blasting out a multispectral wave of energy.
Right. And the research specifically highlights extreme ultraviolet radiation, or EUV.
Alongside streams of charged particles like helium nuclei and heavy ions.
But the extreme ultraviolet radiation is the critical mechanism here. EUV photons carry an immense amount of energy, far more than the standard UV light that, causes a sunburn down here on Earth.
But fortunately for human biology, EUV does not reach the surface of the Earth.
No, thank goodness. It is completely absorbed by the outermost layers of our atmosphere, specifically the layer known as the thermosphere.
The thermosphere.
Yeah.
Which sits roughly between 100 and 1,000 kilometers in altitude.
Yes.
Which means it perfectly overlaps with the low Earth orbit highway, where all of our satellites and all of this space junk are currently flying.
Exactly. The thermosphere is essentially the front line of Earth's defense against solar weather.
So they're right in the thick of it.
They are. Now, to understand why the satellites actually care about this, we had to look at the atomic physics of what happens when EUV hits the thermosphere.
Okay, lay it on me.
So the atmosphere up there is incredibly thin. It's mostly composed of atomic oxygen and diatomic nitrogen. When an extreme ultraviolet photon from a solar flare slams into an oxygen atom in the thermosphere, it doesn't just bounce off.
The atom absorbs the photon's energy, right?
Yes. The photon actually strips an electron away, photoionizing the atom. And that residual energy translates directly into kinetic energy.
And kinetic energy on an atomic level is basically just heat.
Precisely. In the language of thermodynamics, it's heat. The atoms begin moving much faster, colliding with each other with greater force.
So it's heating up the upper atmosphere.
Massively.
Wow.
During a solar maximum, the continuous bombardment of EUV radiation can push the temperatures in the thermosphere to staggering extremes. We're talking about fluctuating between 500 degrees and up to 2,500 degrees Celsius.
Wait, 2,500 degrees? But if you were an astronaut floating in the thermosphere, you wouldn't feel that heat, would you?
No, you wouldn't burn up from the ambient temperature.
Because the gas is too sparse to actually transfer that thermal energy to your skin.
Exactly. The density of the gas is so low that a standard terrestrial thermometer would probably register it as freezing.
Right.
However, the atoms themselves are highly energized. And this brings us to the macroscopic effect, which is thermal expansion.
Oh, because if you heat a gas, it expands. It's the exact same physics as a hot air balloon, just scaled up to planetary dimensions.
That is the perfect analogy. The entire thermosphere physically swells. As those atoms become hyper-energized by the sun, they push against each other and expand upwards.
Fighting against Earth's gravity.
Right, they reach further out into space. And what this means in practical terms is that the density of the atmosphere at higher altitudes increases dramatically.
Okay, so if I'm a piece of space debris orbiting happily at 600 kilometers during a quiet solar minimum, I am basically flying through a near-perfect vacuum.
Right, there's almost no air resistance.
But when the sun wakes up and that EUV radiation hits the thermosphere, the atmosphere literally inflates into my path.
Vacuum disappears, the hot air balloon is swelled into your lane, you are suddenly plowing through a much denser soup of atmospheric gases.
Even though the gas is still incredibly thin by, terrestrial standards?
Even so, because at orbital velocities of 25,000 kilometers per hour, plowing through even a trace amount of extra atomic oxygen generates a massive amount of physical resistance.
Atmospheric drag.
Aerodynamic drag, yes. The friction of those gas molecules hitting the leading edge of the satellite or the space debris actively robs the object of its kinetic energy.
And in orbital mechanics, kinetic energy is life.
It really is. An orbit is just a delicate balance between forward velocity and the downward pull of gravity.
So if you lose forward speed because you are suddenly flying through a thicker atmosphere, gravity begins to win the tug of war.
The object undergoes orbital decay. As it loses velocity, its orbital altitude drops.
And then it falls into slightly lower, even denser layers of the atmosphere.
Which creates even more drag, which slows it down even more.
Yeah.
It is a compounding exponential process that ultimately ends with the object burning up entirely upon re-entry into the lower, thicker atmosphere.
Man, the scale of this mechanism is deeply humbling when you actually step back and look at it.
It really is.
I mean, a localized magnetic snap on the surface of a star 93 million miles away sends an invisible wave of photons across the solar system, which photoionizes oxygen atoms high above the Earth, causing the atmosphere to swell outward, acting as a physical brake pad that drags millions of tons of human machinery out of the sky.
It perfectly illustrates that space is not a disconnected void. It is a highly coupled, fluid dynamics problem. Everything touches everything else.
But understanding the theory of atmospheric drag is one thing. Precisely quantifying it so we can predict satellite collisions is another entirely.
Right, because if the atmosphere swells, you need to know exactly how much drag it actually creates. How fast do things fall?
And to get those hard numbers, you need empirical data over a massive timescale, which leads us to this incredible, unprecedented 36-year cosmic stakeout.
Yes. This is the core of the new research.
So this research was led by Ayesha M. Ashroof at the Space Physics Laboratory, which operates under the Vikram Sarabhai Space Center in Thiruvananthapuram, India. And what her team managed to do is basically use our history of polluting space to create a flawlessly accurate model of the future.
The methodology Ashru's team employed is a masterpiece of observational science. They didn't just, run theoretical computer simulations on a supercomputer.
Right.
They dug into decades of historical tracking data to study the real-world orbital decay of 17 specific pieces of low Earth orbit space debris.
And they tracked these 17 objects over an unbroken 36-year period.
Which is a timescale that's vital, right?
It's completely vital because it allowed the researchers to watch the debris interact with 3 complete 11-year solar cycles.
The 22nd, 23rd, and 24th solar cycles. Exactly. They watched the sun wake up, inflate the atmosphere, go back to sleep, and wake up again. 3 separate times.
Recording exactly how the debris responded to each phase.
Right. And the subjects of this study are fascinating in their own right. These 17 objects were all launched back in the 1960s.
The 60s.
Yeah. We are talking about the heavy, durable remnants of the early space race. discarded upper stages from old orbital launch vehicles, inert payloads that have been dead for half a century.
Just silently circling the Earth every 90 to 120 minutes.
Maintaining an altitude between roughly 600 and 800 kilometers.
But wait, I have to ask about the selection bias here. Because we have thousands of active, multi-million-dollar satellites currently in orbit. We have modern mega constellations downlinking gigabytes of precise telemetry and GPS data every second.
Right, incredibly precise sensors.
So why dig through historical radar archives to track dead metal husks from the 1960s? Why not just use a modern satellite equipped with state-of-the-art sensors?
That is the crux of the genius behind this specific study. Using an active satellite would actually ruin the data entirely.
Really? How so?
Because active satellites have a job to do. They have an objective. They have an assigned operational orbit that they must maintain to provide, say, internet access or take photographs.
Oh, right. So when the swollen atmosphere creates drag and they start to fall, ground control intervenes.
Exactly. When an active satellite experiences orbital decay, operators command the satellite to perform station-keeping maneuvers.
They fire the onboard thrusters.
Right, using chemical or electric propulsion to raise the satellite back up to its proper altitude.
Which completely masks the natural effect of the solar cycle.
It contaminates the data set with a massive human variable. I mean, you look at the altitude logs of an active satellite over 10 years, you can never mathematically isolate how much of the orbital shift was caused by the natural drag of the EUV swollen thermosphere and how much was caused by, an engineer in a control room firing an argon thruster on a Tuesday.
It's noisy data. But the space junk from the 1960s is completely passive.
Completely passive. It has no thrusters, no fuel, no ground control. It is purely ballistic.
It's essentially a perfect, uncontaminated variable.
Exactly. A dead rocket body is responding 100% to the pure physical laws of aerodynamic drag and gravity. So by tracking the exact rate of its descent over 36 years, Ashraf's team could observe the unadulterated influence of the thermosphere's density changes.
They turned discarded trash into the ultimate scientific control group.
They really did. As the researcher stated, this inherent passivity makes space debris an excellent tool for tracing long-term solar effects.
It's kind of poetic, honestly. We left this debris up there through negligence, assuming space was infinite and we didn't need to clean up after ourselves.
Right, out of sight, out of mind.
Yet decades later, that very negligence provided the exact pristine data set required to map the physics of our upper atmosphere.
It's a silver lining to a very messy cloud.
So they have the orbital decay data from the junk. But to prove the causal link, they had to map that decay against the sun's actual behavior, right?
Yes.
They had to cross-reference the 36-year fall of the debris with a 36-year log of solar tantrums.
And for that, they utilized long-term data sets managed by the German Research Center for Geosciences in Potsdam.
Okay. What kind of data do they keep?
This institution maintains incredibly rigorous historical logs of solar activity. They track the daily sunspot numbers, the variations in solar radio flux, which is often referred to as the F10.7 index. It's a highly reliable proxy for overall solar activity.
Right.
And they track the daily variations in extreme ultraviolet emissions.
So they overlaid the trajectory of the 1960s space junk onto the timeline of the sun's magnetic cycle.
They aligned the two data sets, yes.
And when they did that, they didn't just find a smooth, predictable correlation, did they?
No, they didn't. They found something entirely unexpected.
They discovered that the physics of atmospheric drag don't behave like a gentle, sloping hill. They behave like a cliff.
This is the critical breakthrough. This is what is currently forcing orbital dynamicists to completely rewrite their collision prediction models.
Because prior to this, you'd naturally assume a linear relationship, right?
Exactly. You'd think as the sun gets a little more active, the drag increases a little bit. As it gets a lot more active, the drag increases a lot. A straight line on a graph.
But Ashraf's team found a transition boundary.
A transition boundary, yes. The data revealed that space debris loses altitude at a relatively steady, slow pace, even as solar activity begins to climb. The massive, dangerous acceleration in orbital decay only happens when the sun crosses a very specific, identifiable threshold.
The 67% tipping point.
The 67% tipping point. They discovered that when the metric of solar activity, specifically the sunspot number proxy, reaches higher than 2/3 of its maximum peak for that specific cycle, the environment in low Earth orbit violently shifts.
The atmospheric density basically crossed the threshold, and the space junk begins dropping out of the sky at a significantly accelerated rate.
It plummets.
And the nuance of that 67% figure is so fascinating to me because it's not an absolute number. It isn't tied to a specific hard radiation score.
That distinction is absolutely paramount because every 11-year solar cycle has a different personality.
Like some are strong, some are weak.
Exactly. Some cycles are historically weak, producing relatively few sunspots even at their absolute peak. Other cycles are immensely violent, producing hundreds of sunspots.
So if the threshold were an absolute number, say an index score of 150, a weak cycle might never reach it at all.
Right, and a strong cycle might cross it years early.
But the debris doesn't care about the absolute number.
The debris responds to the proportion. The threshold is mathematically tied to how close the sun is to its climax for that specific 11-year cycle.
That is so weird.
It is. Whether the cycle is destined to be weak or strong, when the sun's internal dynamo ramps up to 2/3 of its eventual peak output, the thermosphere undergoes a sudden, nonlinear expansion.
It makes me think of phase transitions in physics. Like, if you are heating a pot of water on a stove, the temperature rises linearly, right? The water gets warmer, but it remains liquid water.
Right.
Whether it's at 20 degrees Celsius or 90 degrees Celsius, the physical state of the environment is essentially the same. But the moment it hits 100 degrees, the boiling point, the entire system violently changes state from a liquid to a gas.
That's a great way to think about it.
The rules governing the water fundamentally change.
Phase transition is an excellent framework for visualizing this phenomenon, because the 67% threshold indicates that the sun isn't just emitting a larger volume of the same radiation. The fundamental characteristics of its emission profile are actively shifting.
So what exactly changes inside the sun at that 2/3 mark? Why does it behave like boiling water?
It comes down to the topology of the solar magnetic field. As the sunspot cycle progresses, the magnetic field lines become increasingly tangled.
Because of the rotation, right?
Right, the sun's differential rotation, the equator spins faster than the poles, so the magnetic lines get wound up. And as it approaches its peak, this magnetic stress doesn't just build linearly.
It builds up tension.
Yes. Around that 67% boundary, the complexity of the magnetic reconnections likely shifts, triggering a disproportionate massive spike in the specific wavelength of extreme ultraviolet radiation.
And as we established earlier, EUV is the exact frequency of light that atomic oxygen in the thermosphere absorbs to create heat and expand.
Exactly. So when that nonlinear EV spike hits the thermosphere, the atmosphere doesn't just gently swell, it violently surges outward.
The hot air balloon basically explodes into the traffic lane.
The boundary layer of density pushes much deeper into low Earth orbit. So those 1960s rocket bodies suddenly slam into a much thicker wall of atomic oxygen. Their aerodynamic drag skyrockets, and they begin to plummet.
The scientific elegance of this discovery is just undeniable. I mean, by knowing this exact proportional boundary, scientists now have a predictable mathematical model.
They do. They don't have to just guess when the drag will suddenly become unmanageable.
They can analyze the upward curve of a new solar cycle, calculate its projected peak, and literally pinpoint the exact month when the 67% threshold will be breached.
It provides a critical early warning system for orbital dynamics. But the implications of this discovery extend far beyond pure solar physics or, tracking 6-year-old trash.
Right, because this transition boundary directly dictates the survival and the economic viability of the modern space infrastructure that our terrestrial society currently relies upon.
This is where the ancient space trash meets the modern billion-dollar tech sector.
Because we've established that the expanding thermosphere does not discriminate. Aerodynamic drag applies the exact same physics to a dead Apollo-era booster as it does to a brand new multi-million-dollar communications satellite.
The atmosphere doesn't care who owns it. And this brings us back to the concept of station keeping and fuel budgets.
Okay, let's unpack that.
So active satellites are assigned to highly specific orbital slots, right? When the sun crosses that 67% threshold and the atmosphere surges into their lane, they experience immense drag.
It's like the junk.
Just like the junk. But to prevent themselves from falling out of orbit, they must fight the atmosphere.
Which means constantly firing their thrusters.
Constantly.
Yeah.
And modern mega constellations like Starlink or OneWeb, they don't use massive chemical rockets for this. They utilize highly efficient electric propulsion systems.
Hall effect ion thrusters.
Yes, typically powered by argon or krypton gas.
Yeah.
And while these systems are incredibly efficient, the fuel reserves on board are strictly finite.
And you can't just send a refueling tanker up to Leo.
No, you absolutely cannot. Once the argon is gone, the satellite is dead. It instantly becomes just another piece of passive falling space debris.
Wow. So the fuel capacity of a satellite basically dictates its entire operational lifespan.
Entirely. When aerospace engineers design a multi-billion-dollar constellation, their economic models project that each satellite will last, say, 5 to 7 years, based on standard drag assumptions.
Okay.
But if you launch that constellation near a solar maximum, right as the sun crosses the 67% threshold, your satellites are suddenly fighting a much thicker atmosphere than anticipated.
Meaning you are burning through your 5-year fuel budget in like 2 years just to avoid falling out of the sky.
Exactly. And we have already witnessed the brutal reality of this in action.
Really? When?
In early 2022, SpaceX launched a batch of 49 Starlink satellites. Unfortunately, they launched them directly into the aftermath of a geomagnetic storm triggered by an active sun.
Oh, no.
Yeah. The thermosphere had swelled, increasing the atmospheric drag at their deployment altitude by up to 50% compared to previous launches.
50% more drag. That's massive. So the drag was so intense that the satellites couldn't overcome it.
They couldn't. The onboard thrusters simply didn't have enough authority to fight the thickened atmosphere.
Yeah.
Up to 40 of those 49 brand new satellites failed to reach their operational orbit and simply fell back into the atmosphere and burned up.
Well, 40 out of 49.
Yes. That single solar event, entirely mediated through thermospheric expansion, cost tens of millions of dollars.
That is just brutal. But let's look at the broader traffic management problem here. Because if the entire atmosphere swells and everything that the 1960s junk, the dead weather satellites, the active Starlinks, starts experiencing heavy drag simultaneously,
Yes.
doesn't the entire orbital shell just like shrink uniformly?
What do you mean?
Like if every single object in LOM drops by 15 kilometers at the exact same time, their relative distance to each other remains the same, right? The whole highway just moves to a lower elevation. So why does this widespread simultaneous drop radically increase the collision risk?
I see what you're getting at. That uniform drop scenario assumes that atmospheric drag affects every object equally.
And it doesn't.
It absolutely doesn't. Aerodynamic drag is heavily dependent on a physical property known as the ballistic coefficient.
Which is the ratio of an object's mass to its cross-sectional area.
Precisely. Drag is determined by how much surface area is pushing through the gas, combined with how much momentum the object's mass carries.
Okay, give me an example.
Let's compare two objects orbiting at the exact same altitude. Object A is a spent rocket stage from 1968. It is a dense, heavy cylinder of solid titanium and steel.
Right.
It has a massive amount of weight and a relatively small cross-sectional area.
It's basically an aerodynamic bullet.
Yes. Now, Object B is a modern communications satellite. To power its electronics, it has unfurled massive, flat solar panels. It is relatively lightweight, but it has a huge surface area.
It's essentially a sail catching the wind.
Exactly.
Yeah.
So when the thermosphere swells and the atmospheric density spikes at the 67% boundary, these two objects react completely differently.
Okay, what happens to the bullet?
The dense rocket stage, the bullet, has enough momentum to largely push through the thicker gas. Its orbital decay accelerates slightly, but it maintains its altitude relatively well.
But the satellite with the massive solar panels catches all of that atomic oxygen.
The drag on the satellite is immense. It rapidly loses kinetic energy and plummets to a lower altitude much, much faster than the dense rocket stage.
So the highway isn't lowering uniformly at all?
Not at all. The objects in orbit are suddenly decelerating at radically different rates, violently dropping into different altitude lanes.
So the entire structural integrity of the ILEO traffic system breaks down. Orbits that were previously safely separated by tens of kilometers in altitude suddenly overlap and intersect.
It creates a chaotic, non-linear mixing of the debris environment. You have dense junk from higher orbits slowly sinking into the paths of lightweight active satellites that are rapidly dropping from even higher orbits.
It's like shuffling a deck of cards at 25,000 kilometers per hour.
That's a terrifying but very accurate way to put it. The collision prediction models that ground control relies upon suddenly become incredibly complex and highly volatile.
Because the variables keep changing.
Right. A trajectory forecast that was mathematically solid on Monday might be rendered completely obsolete by Thursday because a solar flare altered the drag coefficients of 10,000 different pieces of shrapnel in 10,000 different ways.
This forces the operators to recalculate collision probabilities constantly.
Yes.
Which forces them to execute emergency station-keeping maneuvers.
Yes.
Which burns even more of their precious fuel, shortening the lifespan of the satellite even further.
It is a compounding logistical and economic nightmare for space traffic management. And it is all driven by the physics isolated by Aisha M. Ashra's team looking at old space garbage.
It's incredible.
If an aerospace company miscalculates the timing of that 67% solar threshold, their entire multi-billion-dollar satellite network might run out of station-keeping fuel years earlier than projected.
Completely rewriting the economic viability of space expansion.
Completely.
You know, it brings this deeply abstract cosmic science right down to the ground level of human daily life, because it's very easy to look at space as a detached academic subject, just something happening out there in the dark.
Sure.
But the logistics of the modern world are intrinsically tied to low Earth orbit. I mean, the global supply chain tracking cargo ships across the Pacific, the GPS navigation system routing ambulances through city traffic, the precise timing signals required by the global financial sector to process credit card transactions.
It all routes through LEO.
It all routes through LEO. The infrastructure of our hyper-connected terrestrial civilization is entirely reliant on the structural stability of space.
And as this research proves, the stability of space is entirely dependent on our ability to accurately predict the volatile magnetic mood swings of a star located 93 million miles away.
We have journeyed through an incredibly complex chain of cause and effect today. We started in the crowded hyperkinetic shooting gallery of low Earth orbit, examining the constant cascading thread of hypervelocity debris.
Right.
And then we dissected the mechanics of the 11-year solar cycle, exploring how extreme ultraviolet radiation photoionizes atomic oxygen to physically swell the Earth's upper atmosphere.
We then looked at how that swelling atmosphere creates aerodynamic drag, stripping kinetic energy from orbiting bodies and dragging them toward the Earth.
And we traveled to the Space Physics Laboratory in India, where researchers spent 36 years painstakingly tracking the orbital decay of 17 pieces of passive Apollo-era space debris.
And we uncovered their vital discovery.
The 67% tipping point.
The exact moment in a solar cycle's evolution when the magnetic complexity triggers a nonlinear surge in UV output,
causing the atmosphere to rapidly expand and drastically scrambling the orbital paths of every single object in the sky.
It is a remarkable synthesis of astrophysics, fluid dynamics, and orbital mechanics. And honestly, it continually reinforces the profound unintended utility of our past actions.
How so?
Well, the discarded inner relics of the early space race objects we literally abandoned to the void proved to be the only instruments capable of cleanly measuring the raw physical forces of the thermosphere.
Right.
We could not fully understand the existential threat to our modern, multi-billion-dollar satellite networks without consulting the silent telemetry of our 60-year-old crash.
It really is an incredible paradox to end on. As we wrap up this exploration, I want to leave you with one final thought to mull over. Every single week, new rockets are launching hundreds of highly advanced satellites into low Earth orbit, racing to build an impenetrable digital shell of connectivity around our planet. As a society, we tend to view this technological expansion as humanity conquering the natural world, elevating our communications infrastructure above the chaotic forces of nature. But as you use your phone's GPS today or stream a video routed through a mega constellation, remember the physical, invisible tether binding all of that cutting-edge technology to the sun. Out there in the cold vacuum, the survival of our most advanced digital future is fundamentally at the mercy of the ancient 11-year magnetic heartbeat of our star. And we only learned how to listen to that heartbeat by watching the falling, silent ghosts of the 1960s space race.